Alright, welcome to our Chapter 12 video. We're going to start talking about torsion. We've been talking about compression and tension and how much something deforms, stress versus strain. Another type of load or stress that can be applied to an object. Let's say we have a cylinder and we twist it with a force couple or a moment. It's going to cause some twisting to occur, and that's going to cause shear stress that we're going to call tau. So that's going to be in psi or pascals or some other metric prefix of pascals, or possibly ksi. The other thing that's going to happen is, let's say this, we draw a line there and we twist it. That line is going to rotate. And so what we end up with is an angle of twist that we're going to call theta. So theta is going to be our angle of twist. So if you're a structural or mechanical engineer and you're designing some type of drive shaft or structural member that has to resist or transmit torque, you have to make sure that it's adequately large enough so that it doesn't shear apart and break, fracture due to the stress within an allowable factor of safety. We also want to make sure that it doesn't twist too much. That can cause like a backlash in a drivetrain. So we want to minimize these two things. We'll typically be given an allowable shear stress and an allowable angle of twist, and we might then need to size the cylinder that's needed. So our formula for shear stress, tau with the subscript s, is equal to T C over J. Okay, so what do these letters represent? Well, T, and that's not to be confused with the little tau, but big T, capital T, that is equal to torque. C is the radial distance from centroid. So let's see, radial distance from centroid to the outer edge. I'll just say to the edge. So typically we're going to be looking at cylinders. Cylinders have a circular cross-sectional profile. And so if we measure from the center of the circle out to the edge, the center being the centroid, that gives us C. So in other words, C is the radius. Or we could say 2C is equal to the diameter. That's for circular cross-sections. Now there are some other cross-sections, obviously, that you can apply torque to. You could have a hex bar, you could have a square bar, in which case C in a square. If we're concerned about the stress at the outer edge, it would be occurring at the corner. So C in a square would be from the center to a corner. But typically we are just going to be looking at circles. Okay, the last thing here, the last variable in our equation, J, that is the polar moment of inertia. So essentially what the polar moment inertia is, it's a property of the cross-section, so it's based on the shape, not the material, and it essentially is its stiffness or how much it resists twisting. So a higher J value would cause stress to go down. Okay. Now, how do we find out J? Well, J is something that can be calculated. And again, we're primarily going to be looking at circles. So if we look at a circular cross-section, J, polar moment of inertia for a circle, I'll make a notation of that in the subscript, J is equal to pi times d, and although this subscript isn't in the book, I'll put it here, dO, outer diameter, minus di, inner diameter. Each of these diameters we're going to take to the 4th power, and then divide all of that by 32. So what, excuse me, what is the outer and inner diameter? Well, if we are looking at a pipe that is hollow in its cross-section, we're going to have an inner diameter and an outer diameter. So we've got the outer diameter and inner diameter. Now, if we're dealing with a, and this I'll put hollow over here. If we're looking at a solid cylinder with no inner diameter, then the polar moment of inertia formula simplifies quite a bit. It then just simply becomes pi times d to the 4th over 32. Because there is no inner diameter in a solid cylinder, only the diameter. So pi d to the 4th over 32 equals J. This is for a solid cylinder. All right, so let's slide down here and look at example 12.2. So in this we have a circular shaft that has an allowable shear stress. So tau allowable is 83.0 megapascals. Mega is a million, so that's 83. 1, 2, 3, 4, 5, 6 zeros. That's how many pascals. We want to, for part A, assume that we are dealing with a solid shaft with a diameter of 150 millimeters. That is equal to, that decimal place, 1, 2, 3 times, that'd be 0.015 meters. And so we want to know what is the allowable torque? How much torque can we apply to this shaft if it has an allowable shear stress of 83 million pascals and a diameter of, I think I got my number of zeros wrong here. That'd be 123.15. So X that out. It's 0.15 meters. How much torque can we apply to this shaft? Well, our formula for shear stress, tau sub s, is equal to Tc over J. And so if we want to solve for torque, the big T torque is going to be equal to the allowable shear stress times J divided by C. Okay, well, what is J? J is going to be equal to, since this is a solid shaft, it's going to be equal to pi d to the 4th over 32. So that's pi times 0.15 to the 4th over 32. And that is equal to let's see, 1, 2, 3, 4 zeros. So it's 0.00000497. And moment of inertia has units of length to the fourth power, so we converted this to meters, so this is in meters to the fourth power. So our torque formula is going to become 83 million pascals times, I'm going to have to slide over, I'm going to run out of room. Let's move over here. Times 0.000497 meters to the fourth divided by, so if our diameter was 0.15 all the way across, C is basically just the radius, half of that amount. So 0.15 divided by 2 is 0.075. So C is 0.075 meters. So this meter will cancel out one of these, and I'll be left with cubic meters. A Pascal is a Newton per meter squared. So the square meters will cancel out two of these, and I'm just left with meters and newtons. And so let me slide over just a little bit more, give us a little bit more room. So our torque ends up being, when we multiply 83 million by 0.0000497 divided by 0.075, we get 55,000 approximately. I'm getting 55,001, but I'm rounding it off to, well, I guess that's technically only two significant figures, but close enough. And the units are Newton meter. Or we could say, to preserve our three significant figures, 55.0 kilonewton meters. Now, part B of this example problem asks, let me slide back over here. Part B of the example problem asks, well, what if we didn't have a solid shaft? What if we had a hollow shaft with a outer diameter of 150 millimeters and an inner diameter of 125 millimeters? How would that change it? Well, it would change our J value. Everything else would remain the same. So we'd have to recalculate a new J, and this time J would be equal to pi times the outer diameter of 0.15 meters to the fourth minus the inner diameter of 0.125 meters to the fourth divided by 32. That is going to equal 0.0000257, and that's meters to the fourth. So if I then plug that J value in to my torque equation, torque becomes 83 million pascals times 0.0000257 meters to the fourth divided by 0.075 meters, and that gives me an answer of 28,400 Newton meters.